Okay, in this video we are going to be analyzing functions using calculus principles. So we're going to start by drawing a function f. Now suppose we have an endpoint right here, and the function is going to dip down like this. It's going to swing up and then way back down here, and then it's going to get vertical for a split second, and then it's going to end over there. So these are some key points that we are going to analyze. Okay, so first let's focus in on the tangent line slopes. So if we work our way left to right, our tangent line slopes here, notice, are negative. Alright, so we have negative slopes. At this point right here, the graph reaches a low point. Here the slope is horizontal, alright, or the tangent line is horizontal, meaning that the slope is 0. Well, over on the other side, notice that our tangent line slopes are positive. Okay, so we have positive slopes. At this high point we have a slope that is 0. And then back over here we would have more negative slopes. Here's another 0 slope. Here's more positive slopes. Now this point right here is interesting. The tangent line is perfectly vertical. Now if it's perfectly vertical for that split second, the slope is undefined. Alright, sometimes we refer to that as no slope, or we say that it does not exist. Okay? And then after that the slopes become positive. Well, make the connection between slopes of a tangent line and a derivative. Recall that a slope of a tangent line is really just a derivative. So where we have negative slopes, it really means that our derivative, f prime of x, is less than 0. In other words, it's negative. Right here, where the slope is 0, it means our first derivative is equal to 0. Over on this side, our derivative is greater than 0, meaning it's positive. Back up here, our derivative is 0. In this portion of the graph, our derivative is negative, so less than 0. Down here, it would be 0. Then we turn to positive derivatives or positive slopes. At this vertical tangent line, our derivative does not exist. All right, recall from earlier in the course we talked about situations where a derivative doesn't exist. We said if you have a sharp turn, a corner, or a cusp, or a vertical tangent line, those are some situations where a derivative doesn't exist. Other examples included areas where you had discontinuities, like a hole or a VA or a jump. All right, and then back over here, again, your derivative would be greater than 0, would be positive. Okay? All right, so next, let me scroll down here. Let's talk about some definitions. All right, let's talk first about a function increasing or decreasing. Notice that if we were to look back at our graph, in this region where we have negative tangent line slopes or a negative derivative, notice that the function is decreasing. Okay? And notice over here where we have a positive derivative, the function was increasing. Okay? So let's jot down this result. So if f prime of x is less than 0, all right, in other words it's negative, f is decreasing. So notice f prime is used to describe f. And likewise, if our derivative, f prime of x, is greater than 0, so if it's a positive number, f is increasing. So again, notice that we are using the derivative to tell us some information about the function f of x. All right, let's look at another concept. We're going to define something here. We're going to define critical points. All right, critical points are, and you have to know this definition. A lot of times you'll see questions that will ask you to determine the critical points. So you have to know that these are points where f prime of x, your first derivative, is equal to 0, or where f prime of x is undefined. All right, in other words, it does not exist. Okay, so critical points are points where our derivative has a horizontal tangent line, all right, or our function, I should say, has a horizontal tangent line, or has a vertical tangent line. So in other words, the derivative is equal to 0 or is undefined. So if we go back up to our graph here for a moment, let's identify our critical points by just writing CP, all right, by those points. Well, where I have this minimum value, this is a critical point because the derivative was equal to 0. Here's another spot where the derivative was equal to 0. This low point was a critical point, and finally that point right there where we had an undefined slope, that was a critical point. Okay, so it looks like we have 4 critical points on that graph. All right, next let's talk about what are called relative extrema. Let me grab a different color here. Sometimes a question will ask you to find the relative extrema. All right, well, that sounds like your extreme values. So when we talk about relative extrema, we're talking about a relative, which, by the way, sometimes you'll see the word local. All right, a relative or a local min slash max. Okay, so relative min, relative max are points where it sounds exactly like you would think is where you have a low point or a high point. Let's use a more formal definition here. So we have a relative min slash max at, let's say, x equals c, if f of c is the smallest or the largest, if it's a max, all right, is the smallest or the largest value of f near c. All right, so we're going to have a relative min at some x value, which we're calling c, if the y value, f of c that is the smallest value of the function near c. All right, so in other words, if you were to kind of zoom in on a particular area, all right, if I were to zoom in on this point right here, this endpoint, within that little neighborhood, within that little local region, okay, look at where I boxed it in, okay, that is the highest point. All right, so this we call a relative max. Down here, if I were to box in this little window, look at that local region. Well, that is a low point. It's a minimum point, so we call that a relative min. It has the smallest y value within that region. Likewise, up here, we have what we call a relative maximum, because again, within this region, it has the highest y value. Down here, we would have another relative minimum, and at our endpoint here, within that little region, that is the highest point. So we have a relative max. Okay? So most of the time, your relative min and your relative maxes are going to occur at these low or high points where the derivative is equal to 0. The endpoints, the derivative is not equal to 0 there. It's kind of a special case. So we're going to further define relative mins and relative maxes in the following way. Okay? So if our derivative, f prime, changes from negative to positive, and f prime of x is equal to 0, right, we have a relative min. So we're going from a function that is decreasing to increasing. Okay? So that's going to give us a relative min. And likewise, if our derivative changes from positive to negative, and f prime of x is equal to 0, we have a relative max. Okay? One more term here to be aware of, and that is absolute min or max. So we talked about finding a relative min or max. All right, that's within smaller windows of the graph. An absolute min or max, this is exactly what it sounds like. It's the absolute lowest or the absolute highest point. So this is the smallest slash largest of all the relative min or max. So if we go back to our diagram real quick, all right, think about which points would be considered the absolute max or the absolute min. Well, what is the absolute highest point? Well, that occurs right here. So yes, this is a relative max, but it's also the absolute max. It's the absolute highest point. And down here, down here at this point, we have our absolute lowest value, so that is our absolute min. Notice that sometimes the absolute min or max occurs at an endpoint, and other times it occurs somewhere in the middle of the function. Okay, so let's take a look at an example. All right, so if you want to flip your page over, all right, what we're going to look at now is what we call the first derivative test. Okay. Suppose in this example we have y equals negative x cubed plus 3x squared plus 5, and we wish to find where, this is all without a calculator, find where f, alright, so this is f of x, I know I wrote y equals, but pretend it's f of x, find where the function increases slash decreases and x values of relative min and max. Okay, that's what we're looking to do here. Alright, so we're going to simultaneously list out some steps as we do this. Alright, and again, this is known as the first derivative test. Alright, so as you would suspect, we're going to need to find our derivative. So step 1 is to find f prime of x. Alright, so if we do that, alright, I'm just going to get rid of this y and turn it into f of x. So f prime of x is equal to negative 3x squared plus 6x. Okay, nice easy derivative. From there, keep in mind that we said that our points of interest, which we called critical points, are points where the derivative equals 0 or is undefined. Well, with this polynomial function, there are no points where it's undefined. So what we're going to do in our next step is to set f prime of x equal to 0 and solve. Alright, so I'm just going to say here, find critical points. Alright, you may also need to find where your derivative is undefined. Okay, so I'm going to just add here, find where f prime of x does not exist, 2. Alright, if any. Alright, that's not applicable here because, again, it's a nice polynomial function. The derivative is going to be defined everywhere. Okay, so 9 times out of 10, you're just going to take your derivative and you're going to set it equal to 0. And you're going to solve. So pull out a GCF of negative 3x. Alright, set each factor equal to 0. And solve, we get 0 and 2. Okay, these are critical points. Okay, or I'll just say CP. Okay, it's a critical point. Alright, so from there, recall from last year, we made a sign diagram. So make f prime of x sign diagram is our third step. Alright, so what does a sign diagram look like? Well, this is where we're going to make a number line. I'm going to label it f prime. And I'm going to mark off the x values. Now it's a number line, so it has to go left to right from least to greatest. Okay, so we have 0 and 2 down there. And we know that the derivatives are 0 at those 2 points. Okay? So, because again, we solved and we got these answers, alright, where the derivative was equal to 0. So this is where we're now going to plug in some points on each side of 0 and 2. So we're going to plug into your derivative. Now, yes, this is a derivative formula, alright, but so is this down here. You want to use the factored version of it. It'll make your life a lot easier, especially if you don't have a calculator. So something to the left of 0, plug in something like negative 1. Alright, so if I plug in negative 1 into this factor, negative 3 times negative 1, well, that's a positive. And if I put negative 1 into this piece, alright, negative 1 minus 2, that's a negative. When I multiply those, I get a negative for my final result. Alright, now let's find a number between 0 and 2. How about 1? So put 1 into this first factor, it's a negative. Put 1 into this piece, it's another negative. Multiply, you get a positive. Alright, put a 1 into, or I'm sorry, put a value greater than 2 in, such as 3. So put a 3 into this, we have a negative, and then a positive, which makes that a negative. Please don't assume that we are always going to alternate in signs. You'll see examples where that is not going to be the case. Okay? So the last step here is to interpret. Alright, so this is where we're going to answer the questions. We're going to analyze what these signs are really telling us. Well, recall from earlier, we said that if a derivative is negative, it meant that f is decreasing. Alright, so f, not f prime, but f. See, we're using f prime to describe f. The derivative is a tool used to describe f. Alright, this is known as the first derivative test. We're testing out some concepts. We're trying to figure out what's going on with f. So this is telling us that f is decreasing from negative infinity up to the x value of 0, and then again from 2 to infinity. And likewise, f is increasing from 0 to 2. So we're using interval notation there. Alright, and the last thing the question wants us to find is where we have a relative min or relative max. Well, if we were to take a look at what this function really is looking like, if the negative derivative means it's decreasing, we said, and then it's going to turn and it's going to increase. Alright, and then slightly after that, alright, if it's increasing, alright, it's going to turn and eventually decrease. So what we really have here at these 2 points are a min and a max. So f has a relative min at x equals 0, and we have a relative max at x equals 2. So again, if the derivative goes from negative to positive, we have a min. If it goes from positive to negative, we have a max.